Throughout this course, we're going to be using vectors to help us perform many different other calculations. And because vectors have direction and magnitude, anytime we use a vector, the magnitude and direction of that vector get incorporated into whatever calculation we're doing. But many of those calculations, we want to use the vector only for its direction, and we don't want its magnitude having an effect on our calculation. So when we only want to use a vector for the sake of incorporating its direction into our calculation, what we need to do is we need to create a unit vector. And a unit vector is a vector that's just 1 unit long or has a magnitude of 1 unit. In order to do that, we're going to have to first figure out what the magnitude of our vector is. So we've already talked about this, how to find the magnitude. If we have vector v and its components are v1 and v2, then the magnitude of v is the square root of v sub 1 squared plus v sub 2 squared. We don't want this magnitude being included in our vector when we're using a unit vector. So that the way that we create a unit vector, and almost always you will see a unit vector exclusively using the name u. We can make a unit vector out of vector v if we divide the components of vector v by the magnitude of vector v, which means division is just the exact same as scalar multiplication, because you can think of it, instead of dividing as by multiplying by a fraction, that scalar just gets distributed to all of the components. So our unit vector would have components v1 divided by the magnitude of v, v2 divided by the magnitude of v. So for our first example, we are going to find a unit vector in the direction, which means we like the direction of the vector we're given, but we want to shrink it down to only have a magnitude of 1. So I want to find a unit vector in the direction of vector v, which has components 5, -2. And just to kind of drive home this concept, I'm going to draw the original vector, and then I'm also going to draw the unit vector that we create. So the vector 5, -2 goes from the origin out to 5 on the x-axis and -2 in the y-axis. So that's our original vector v. In order to change this to a unit vector, we are going to have to first find the magnitude of v, which is the square root of 5 squared plus -2 squared. And we get square root of 29. Now 29 is not a perfect square, and there's no way to simplify square root 29 to anything simpler. And you don't want to change this to a decimal almost always, unless the directions specifically say that you can find an approximation or use decimals. You want to leave all of your answers exact. So the unit vector that's in this exact same direction, we would take vector v and we would divide all of the components by the magnitude of v, which we just found was square root 29. So our numerators are going to be the original components, but now we're going to introduce a denominator that is equal to the magnitude. So a unit vector in the exact same direction as v has components 5 divided by square root 29, negative 2 divided by square root 29. Now, I just told you that we don't want to change this to decimals unless we're told to, but for the sake of graphing it, I am going to change it to a decimal just for the ease of graphing. And very often when I'm making approximations or doing rounding, I will use my squiggly equals, which means approximately equal to. So like I said, just so that I can graph these efficiently, I'm going to change them to decimals. 5 divided by the square root of 9 is about 0.93. And negative 2 divided by the square root of 29 is approximately negative 0.37. If we graph that, and I'm going to graph it in a different color so we can distinguish it from v, 0.93, that's just a little bit before 1. Negative 0.37, that's down about 1/3 of a unit. And we should get a point that is on vector v. If it's shorter, it should be on the vector that we've already drawn. So vector u is the red vector. It points in the exact same direction as v, which means it's right on top of it. But what we've done is we've shrunk it down to be just 1 unit long. Now, if we like the direction of vector v and we just don't want its magnitude having any effect on our calculation, we have to shrink it down to that unit vector. This unit vector, you can check, should have a magnitude of 1. So if we find the magnitude of u, that means we want to square the components and then add them together. So when you square a fraction, remember, just square the top, square the bottom. This is 25/29 and 4/29, which makes 29/29, which is equal to 1. So exact same direction, but now it's only 1 unit long, and the magnitude of this vector will not have any effect on any calculations we use it for, but its direction will be incorporated into any answers we get that use it. There are two very special unit vectors, and these are called the standard unit vectors. Our standard unit vectors only have one component, or they only have magnitude in one direction. So we do have the word unit vector in here, so it's going to be a vector that's only 1 unit long. And standard, what makes these guys standard is that they only have one direction associated with them. So if we go exactly 1 unit in the x direction, that is a unit vector because it's 1 unit long, and because it only contains the x direction, it's one of our standard unit vectors. We call that vector I. Now remember, the way we get components, if it's in standard position, which it is, it starts at 0, 0, the components are really just your terminal point. So the terminal point for our standard unit vector I, which is just a vector with magnitude of 1 that points only in the positive x direction, the terminal point is 1, 0. We also have a standard unit vector in the direction of y. So if I get a vector in standard position and I go 1 unit in the y direction, we call that vector j, and that terminal point is 0, 1. Those are our standard unit vectors. And all of the vectors that we so far have been writing in component form, if we wanted to, we can write them in a little bit more of an algebraic format using i's and j's. So let me show you how exactly we do that. Now this process I'm going to show you is really exaggerated, and you wouldn't go through all these steps when you did this. You will see when we compare where we started and where we ended that it's really, really simple. Our goal here is to express a vector that has components -4, 1, in terms of standard unit vectors. Now you need to be really careful because this sounds similar to what we just did in finding a unit vector, but that inclusion of the word standard automatically means we want to express this vector using i's and j's. What I'm going to do here is I'm going to use those properties that we learned of how you add, subtract, multiply vectors, but I'm going to use them backwards. So vector v is equal to -4, 1. We can separate those two components into their own vectors, and we can say that this vector is the sum of -4, 0 and 0, 1. So I just like undid an addition problem. So if you check it and go that direction, you see that it's true. -4, 0 plus 0, 1 is -4, 1. Now we also can pull out the magnitude of those vectors. We can factor it out. So I can say this is equivalent to -4 times 1, 0 plus 0, 1. My goal was to get this in terms of my standard unit vectors, which have components 1, 0 and 0, 1. So now that we have this in that form, 1, 0 is equivalent to the standard unit vector I. So this is -4 I. And then 0, 1 is equivalent to a standard unit vector of j. So this is just plus j. So I don't expect you to go through this process every time we're asked to change something to a vector that uses standard unit vectors. But if you compare where we started to where we ended, you will see there's a very simple way to just jump from the beginning to the end. Your components, when you are written in component form, just turn into coefficients for your I and your j. So the -4 component is now just a -4 coefficient on I, and your 1 component is an imaginary 1 component on j. If you think back to algebra, when we have a coefficient of 1, we usually don't write it. But we could write it if it makes more sense to us, if we're more comfortable that way. But we typically don't write coefficients of 1. I'm going to do one more real quick, and I'm just going to jump straight from the beginning to the ending. So this time we're going to write the vector 5/2 and 9/4 in terms of standard unit vectors. Now we could go through that whole algebraic process, but all it's going to boil down to is that 5/2 is going to be the coefficient on the I, 9/4 is going to be the coefficient on the j. So we're going 5/2 in the x direction, and our standard unit vector I points solely in the x direction, and then we're going 9/4 in the y direction, and j is the standard unit vector that takes us in the y direction. So it's as simple as that. Now, both of these formats are equally as popular. You are going to see both of these formats throughout all of the problems that we use throughout the semester. So it's important for you to just know that they mean the exact same thing. We are going to wrap up this section with a discussion and then an application of how vectors are actually used in real life. You probably never are going to be given an application problem where the vectors are already given to you in component form. When vectors are used in real life, they're really given as just their direction and their magnitude. It's much more intuitive to think about a vector based on how big it is and what direction it points in. The problem with this, though, is when we do calculations, we are not allowed to combine vectors unless they point in the same direction, unless they have the same direction. Vectors must have the same direction or exact opposite. In order for us to algebraically combine them. And that's what the components do for us. The components take a vector's direction and magnitude and they split it into an x and a y, a horizontal component and a vertical component. So one thing that we need to get proficient in is switching a vector back and forth between its component form and its direction and its magnitude. And this is fairly simple if you know some basic trigonometry. If we let this horizontal side of our right triangle represent the x component of our vector. Previously, we called this v sub 1. It is very also often called v sub x. And v sub 2 is often called v sub y. So this horizontal side, just like our x is the horizontal axis, is our v sub x. And then the vertical side is our v sub y. The magnitude and direction of this vector are represented by the angle here, theta, and the hypotenuse. So there's some very simple trigonometry that relates these four values together. So v sub x is our horizontal component. V sub y is our vertical component. And these two are often used together. The other option we have is describing a vector using magnitude and direction. And if you're working on a problem that contains multiple vectors, sometimes that theta will have a little subscript letting you know that it's the direction for vector v. If we were working with a problem that also had a vector w, then the direction for w would be theta sub w. So these are two very important ways that we represent vectors. Magnitude and direction is the most common way that we see vectors used in real life, but component form is the most common way that we use them for calculations. So we're going to have to switch back and forth very often between these two formats. So if we know v sub x and v sub y, we know the components, and we want to get magnitude and direction, you just need to think of this as a right triangle. We know the legs of the right triangle, and we're trying to find the hypotenuse. So like we said earlier, magnitude is just like the Pythagorean theorem. So we can take components and find magnitude by doing the Pythagorean theorem, v sub x squared plus v sub y squared. If all we know is our components and we want to find the direction theta, anytime you are trying to figure out a relationship between sides of a right triangle and then an angle within the triangle, it's going to involve trigonometry. So based on where I've drawn theta, v sub y is the opposite side and v sub x is the adjacent side. So we need to figure out which trig function uses the opposite side and the adjacent side of a right triangle, and that's tangent. So tangent of theta is opposite over adjacent. And if we wanted to solve for theta, then we would just use tan inverse. When you do that, though, especially on your calculator, you need to be very careful because your calculator does not always put this answer into the correct quadrant. So you need to make sure that you're looking at the sign on your v sub x and v sub y and making sure that you're using the correct quadrant. So just as a quick review, if both of your components are positive, your direction angle should be in quadrant 1, which is going to be somewhere between 0 and 90. If the x component is negative, but the y component is positive, then you're in quadrant 2, and your angle should be between 90 and 180. If both of your components are negative, that would put you down in quadrant 3, and your angle should be between 180 and 270. Oops, sorry. And then for quadrant 4, we've got a positive x value, a negative y value, and angles in quadrant 4 range between 270 and 360. When you use tangent inverse on your calculator, it's going to give you a reference angle. It's going to tell you how far away you are from the closest piece of the x-axis. So it might give you an angle. If you know you're in quadrant 2 or quadrant 3, then it's telling you how far away from 180 you are. If you are in quadrant 1 or quadrant 4, then it's telling you how far away from 0 you are. We usually use just standard position angles, 0 to 360. Your calculator will very often give you a negative angle for quadrant 4, and you can fix that just by adding 360 degrees to it. So suppose we've got this the other way around. Suppose we know magnitude and direction, but we want to find components. Just like before, in the case of a right triangle, if I know the hypotenuse and I know one of my angles, which is going to be my direction angle, we're trying to find the legs of the triangle. And when we start out this problem, we have a side and an angle. And like I said a minute ago, anytime you're trying to find relationship between sides and angles in a triangle, it's going to involve trigonometry. And we want to solve for these one at a time. So first I'm going to solve for v sub x. If I know theta and I know magnitude of v, which is the hypotenuse, we want to find v sub x. Well, based on where theta is drawn, v sub x is adjacent, and our magnitude is the hypotenuse. So which trig function uses adjacent and hypotenuse? Cosine does. So cosine of theta is adjacent over hypotenuse. But this is not the formula we're going to use. We're using this for the sake of solving for v sub x. So to solve this equation for v sub x, I have to just multiply that magnitude over. So v sub x is the magnitude of your vector multiplied by the cosine of the direction. V sub y is worked out very similarly. The only difference is based on where theta is located. V sub y is the opposite side. So the trig function that uses the opposite side in the hypotenuse is sine. So sine of theta is V sub y over magnitude of V. So to solve that equation for V sub y, we would multiply over the magnitude of V and get V sub y equals magnitude of V times sine of theta. So this is how we can use magnitude and direction to get components. And then a formulas earlier, how we could use components to get magnitude and direction. With our Pythagorean theorem and our tan inverse. So we're going to look at an application problem where we have to use all of these formulas. Because in most application problems, you're going to be given magnitude and direction, but before we can do any sort of algebra with our vectors, we have to change them to components. I'm going to set up a table. I know some of our physics instructors use this particular table to do these calculations, and I think it would be helpful if we're all doing them similarly. The table is not required, but it's just a nice way to organize all of your information. We want to find the speed and direction of an airplane with relation to the ground if it is traveling at 450 miles per hour in a northwesterly direction. And it encounters a wind blowing at 50 miles an hour, coming from the west. Now there are a couple of little tricks in this problem, but I'm not doing it on purpose to try to trick you. These are common ways to represent both an airplane's magnitude and direction and a wind's magnitude and direction. In meteorology, when we talk about winds, we don't describe the direction they're blowing in. We describe the direction they're coming from. And that's a very important thing to recognize here. They're telling us the wind is coming from the west. But when we represent vectors, we want to know what direction it's going to. So they tell us it's coming from the west, and what that means is that it's blowing to the east. So we want to start, what we've been given is magnitude and direction for two vector values. Now that wind is going to affect this plane's speed and direction, and we want to know what happens when the plane's speed and direction gets acted upon by the wind's speed and direction. What's actually going to happen to this airplane? So we've got two different vectors here that we want to combine. So it's very common for us to make a table to organize all of this data. We're going to name our vectors so that we can keep track of each of them. These vectors have a particular magnitude and direction. And in order to do these calculations, we're going to have to split them into components, v sub x and v sub y. So The first vector that we are presented with in this problem is an airplane. Its magnitude is 450 miles per hour, and we are told that it is traveling in a northwesterly direction. So north is up and west is left. So if you go equally up and left, that's going to put you 45 degrees into quadrant 2. And 45 degrees into quadrant 2 is 135 degrees. And I'm just using standard position angles, like we learned in trigonometry class. We also have a wind. It's got a magnitude of 50 miles per hour. It's coming from the west, which is 180 degrees, which means our vector is actually going to the east, which is 0 degrees. And our goal is to combine these. And when you combine vectors, the answer is called the resultant. In order to get v sub x and v sub y, we're going to have to use those sine and cosine formulas. So the first thing we're going to do, I'm going to describe the direction that we're going to go in. We're going to use magnitude and direction to get components. Once we have our vectors and components, we'll then be able to add those components together to get components for the resultant. And then once we have components for the resultant, we want to answer this question back in terms of magnitude and direction. So we fill in this table in a circular motion, a circular counterclockwise motion. So I'm very quickly going to fill in our components. So remember, I'm going to write one of them out for you. To get the x component of a vector, we need to do magnitude times cosine of the angle. Make sure your calculator is in degree mode. Otherwise, you will get a completely different answer from radians. And then we need to find x and y components for both of these vectors. We want to fill in all 4 of these boxes here. So I've just gone ahead and used my calculator to figure out all of these values, and I filled the values into the table. I just used those cosine and sine formulas that we talked about a few minutes ago. And now that we're in component form, the x component for our airplane and the x component of our wind, those components point in the same direction, so that we are now allowed to actually combine the components. So we want to combine negative 318.2 and 50. And our y components point in the same direction as well. So we can combine 318.2 and 0. That's going to make the components of our resultant vector negative 268.2 and 318.2. Now we've got components for the answer, but we typically are going to answer the question the same way that it is asked us. Since this question was asked of us in magnitude and direction format, we want to answer it in magnitude and direction format. So we've got a vector that has these components. So now we need to find the magnitude of that vector, and magnitude is just our Pythagorean theorem. So we square our components and add them together under a square root. And we have a negative x component and a positive y component. That tells me my final answer should be in quadrant 2. And that's an important thing to note. You can't always trust exactly what your calculator tells you. You need to use the information from the calculator to get the answer into the format that you need it. But I am going to do tan inverse in order to get theta of my y component divided by my x component. When we run these calculations, I get a magnitude of about 416.2. And for theta, my calculator is saying about negative 49.9 degrees. This is a reference angle. This is not my answer. This angle references where I am with respect to the closest piece of the x-axis. So we've already identified that this is a quadrant 2 angle, which means negative 49.9 is my distance from the 180 degree line, or my distance from the west line. So there's two ways that we can write this. In order to change this angle to the actual angle we want, we would have to add 180. Anytime you're in quadrant 2 or quadrant 3, you can take that answer from the calculator and add 180. And when I do that, I get 130.1 degrees. So that would be our answer as a standard position angle. The other option would be that we are north, we are north 49.9 degrees of west. So from the west line, we need to move north 49.9 degrees. So that's another way you might see this written. Either one is perfectly fine. It changes from problem to problem. And that is our final answer. So the airplane, the pilot is actually steering this plane 135 degrees at 450 miles per hour. But once it encounters that wind is pointing in a different direction, which means it's slowing us down. So even though the pilot is trying to go 450 miles per hour, the wind is slowing us down to 416.2. It's also pushing us slightly off course because it's pointing in a different direction. The pilot is steering us 135 degrees, but once we come in contact with the wind, it's putting us off about 5 degrees, and the direction of the plane actually ends up at 130.1 degrees.